Good afternoon, everyone. So today I'd like to introduce David Jorm. David's been in the tech industry in Australia for more than 20 years. We just worked out we'd met a long time ago. We're not going to say how old we are. From government, he's worked with vendors, and now he's at a fintech venture scaler, X15. Today he's talking about Log4SHELL, which is the early Christmas present of a lot of us last year. So please welcome David.
Hey everybody, mic level's good? Okay, great. I tend to move around the stage a bit, so I hope that's okay for people viewing at home. Just a little intro on me if you don't know me. I'm the head of security for X15 Ventures. X15 Ventures is the financial technology arm of the Commonwealth Bank. So the traditional banking model is under threat by things like cryptocurrency, afterpay, all this kind of stuff. So in order to compete in that space, they've funded a venture scaler, and we create fintech ventures that then try and integrate back with the bank's customer base. And I'm the head of security for that arm of the bank. Previously, I've been a penetration tester and a product security engineer. And previously to that, I was a software developer. And previous to that, I was an aviation meteorologist. My claim to fame, I think I've been saying this for 10 years now, but it's still true, is anytime you go on a plane in Australia and the captain comes on, tells you what the weather is when the plane's about to land, I coded the system that transmits that information into planes, and it's coded entirely in Oracle PL SQL. It's probably some of the worst production code ever, but it's still there. I also teach cybersecurity at UNSW. I'm currently teaching a master's level course online, and I've been speaking at AusCERT for a long time. This little photo here is my favorite AusCERT presentation, which was in 2014, I think, when I was doing the stuff on the North Korean missile tests. And then afterwards, some ASIO dudes hit me up out the back, and they were like, don't go to North Korea. That was fun. This is not nearly as interesting. But it's an interesting story. And it's a story about Java deserialization, RCE, and a story about how the Log4SHELL vulnerability came about and the whole history of that. So the countries that are highlighted on this map, no, it's not countries that use the metric system or something. That's just, don't use the metric system. That's just Liberia and America. It's countries that have people involved in this story. So it's been a really interesting story, and we'll go through it chronologically. And it begins here in Australia, in Brisbane, at the Red Hat office, where me and my colleague Arun were sitting there at about 6 o'clock one night. I think it was a Friday night, I can't remember, I think it was. And we got this email that was entirely in Japanese. Like the subject line, the entire email body is in Japanese. But it's got all these strings in it, like exploit.class and Java, payload.java and stuff. And we're like, okay, what's this? We ran it through Google Translate, and it didn't really give us anything meaningful. We could figure out it was a vulnerability report, but anything that technical, Google Translate's a little bit useless. So fortunately for us, at the time, Red Hat's Asia-Pacific headquarters was in Brisbane, and we had the localization team that would do the translation of all like the kernel docs and stuff from English into Asian languages, including Japanese. So we went to the head Japanese translator, gave her this email, and she perfectly translated it into English for us. And it was the report of the first ever Java deserialization RCE vulnerability. And that vulnerability was CVE 2013-2165 in JBoss rich faces. Now, we got the report because JBoss was an open source project that was auspiced by Red Hat. So somewhere on the jboss.org page, it said report security issues to secalert at redhat.com, and therefore we got it. The guy who reported it, so the second country on that map, Japan, Takeshi Terada, I just want to take a second to point him out. Nobody's heard of Takeshi Terada. He's never spoken at a conference, he doesn't publish anything in English, he doesn't write white papers, and he doesn't really have CVEs. But if you go onto the JVN, which is the Japanese equivalent of the NVD, of the CVE database, because they have a kind of closed tech ecosystem, both in Japan and China. So in Japan, they have the JVN, in China, they have the CNVD, their own equivalent of the CVE or NVD database. If you go onto the JVN, he's all over it. Amazing security researcher that nobody's heard of. And he found this whole vulnerability. This is the most amazing thing. This whole vulnerability that unpacked an entire class of vulnerabilities, he found us doing a client pen test that happened to be against a target running JBoss rich faces. Far out. So a flaw was found in the way that rich faces handled deserialization. Now, rich faces is an MVC web platform, and it maintains state with the client using a serialized string. Similar to like ASP.NET uses ASP.NET session state. It used this serialized string that would be passed in, view state. They call it ASP.NET view state. They use this view state string that would be passed between the client and the server to maintain session state. And it turns out that that string was a serialized Java object, a native serialized Java object. So that was the root cause of the vulnerability. Now, why does that allow you to get RCE? So any classes that implement java.io.serializable can be serialized automatically by Java. It's got its own native binary format that it will serialize the data into. It's not XML, it's not JSON or YAML. It's this native binary format. And all they have to do is implement serializable. So if you've got a simple class that just has some methods and attributes, you just implement java.io.serializable, boom. Nothing else to do. If, however, you wish to implement some custom logic that will occur upon deserialization of this object, there are two methods that are provided to you by that serializable interface. One called readObject and one called readResolve. If I remember correctly, readResolve executes first. readResolve executes later, according to my slide. readObject is executed first. readObject is the one that's nearly always used. readResolve seems to be some quite obscure use case. But you can implement things in there, like say you're deserializing something that represents a file on disk, and you actually want to then put the data of the file on disk during deserialization, you would implement that in the readObject method. And it's also notable that when you serialize objects, all of the access modifiers don't matter. So private, protected, member variables, you can set whatever you want when you serialize an object. So that was part one, was you had JBoss rich faces would maintain its view state using a serialized object. Part two was the fact that these serialized objects have a readObject method that can contain custom code. Part three was that Apache Commons file upload, which is it is what it says on the label. It's a library that allows you to do file uploads in web apps, has a class called disk file item in it. That is a disk file item that represents a file that you're uploading. And when you deserialize it, it writes that file to the temp directory on disk. Does all that for you automatically. And it does that securely by correctly setting up a temporary directory and a temporary file name and putting the file there so that you can't just write to an arbitrary location. However, the fourth part of this is that the actual underlying JRE, Java Runtime Environment code, that writes that file to disk calls native C code. And that native C code had a poison null byte flaw in it. So in C code, a string in memory is just represented as a chunk of arbitrary memory that's terminated with a null byte. And that's how you know the string is ended. So if you can inject a null byte somewhere into a string, in the middle of the string, then when that's being read in memory, it will be interpreted as the end of the string. And you can then truncate the file name. So that's a very old school vulnerability from like the late 90s. So by combining all of these things, you could create a view state in rich faces that has a serialized object that is a disk file item. That disk file item has a file name, and that file name has a poison null byte attached to it, so that when it attempts to concatenate that string with the temporary path that it's going to write to, it interprets the end of the string, and therefore the string that you have written as the file name is the absolute file path of that, and that's where it will be written on disk. So now you create a serialized instance of like shell.jsp, you control the path to which it's written, and now you've got remote code execution. And he found all of this doing a client pen test. It's like, so that's how this whole thing started in 2013. And around 2015, the next country on that map was the United States. Chris Frohoff picked this work up and started to realize that this was a more extensive issue, because we'll get to the mitigations in a minute, but that all got patched. But what he started to realize was that it wasn't just the case of disk file item, where there was this combination of the fact it was directly representing a file on disk and a poison null byte flaw in the JRE, which all got patched. But this whole design pattern was fundamentally insecure. And it looks sort of like ROP, that what you need to do is serialize an object graph. And that object graph has a source that is some sort of serializable object that has a custom read object method in it. And then you need to create, in that object graph, a series of other objects that will call into other methods of other objects. That read object method will call method X of class Y, will call method Z of class B. And if you finally can then, in that object graph, land into a sync method that will allow you to control a call to code exec, then you will get code exec. And this sort of style of thing was coined as property-oriented programming, rather than return-oriented programming for ROP, it's property-oriented programming. And you could create what they call gadgets of these serialized class instances or object graphs that would land you in RCE. This was originally identified as an exploitable pattern in PHP by Stefan Esser several years earlier, and then Chris Frohoff picked it up and turned it into Java. He created this project, which some of you may have heard of, called Why So Serial, where he's enumerated all of the known instances of these gadget classes, and then created a tool that allows you to easily instantiate payloads against them. So if you have any of these vulnerable classes on the class path on the server side, then you can create a payload that will do it. Now, this is an important point to note. This all relies on what's on the class path on the server side. When you're providing these serialized objects, you're not defining the structure of the object and then giving it to the server. You're defining an instance of an object type that the server should already know about because it's on its class path in memory. So it relies on there being an exploitable gadget chain that is on the class path of the target application. But if you look at some of these things, like commons collection, extremely widely used, Spring, extremely widely used, file upload, extremely widely used. So many applications will have these gadgets on the class path. And therefore, if they are deserializing untrusted user-supplied input, you will get remote code execution. So that was the state of play circa 2015. And it was the conclusion of the community that anyone who's deserializing untrusted user-supplied input in Java is vulnerable to RCE because there's an unknown number of gadget chains. We've already enumerated a couple of dozen of them. There could be infinitely many more. So just don't deserialize untrusted user-supplied data. My view back in 2014 was somewhat different. When we originally patched this issue, and this is an excerpt from a blog post I wrote on the Red Hat security blog, was that the vulnerability, yes, existed in the deserialization of untrusted data, but it also existed in disk file item, in this class that exposed this vulnerable use case, and that every gadget chain was actually an instance of a vulnerability, not just the deserializing class, and we should patch both. This was resoundingly rejected by everybody else in the security world. They said, no, that's insane. It's like saying that every piece of code is vulnerable to ROP. You can't do that. The deserialization is the vulnerability. So even though I assigned a second CVE to disk file item and they patched it, the Apache Software Foundation didn't recognize that CVE and just said this is a non-security fix. This is like a hardening fix. And so all the other gadgets that got exposed never got patched and never got CVEs. Okay, so moving forward, enter JNDI and LDAP. So that was just the history of how we got to Java deserialization vulnerabilities. We're going to build up to the picture of how we got to Log4Shell. JNDI is the Java Naming and Directory Interface. And all of these acronyms, if you go back to the mid-90s, Sun Microsystems, when they used to run Java and before they got destroyed by Oracle, they used to have this great vision of the network is the computer. I think that was their tagline. And the way they wanted to implement this was to have, I guess it was an early version of web services, that you would have small pieces of code hosted on different servers, distributed across a network, and that they would make interoperable calls to each other. Now, web services implements that using largely XML and HTTP as encoding and transport mechanisms. Before that existed, all of these things, LDAP, RMI, Corba, JNDI, were created as mechanisms to allow for this distribution of code across computer networks. The basic way that it works is JNDI allows you to look up a remote instance of some code. It's totally overcomplicated. Everything to do with Java is totally cooked, by the way, if that's not obvious. So overcomplicated. So JNDI lets you look up an arbitrary remote code resource. LDAP is an implementation of how you can look up a remote code resource by specifying it as an item in an LDAP directory. which then points you to a URL of where that resource is actually hosted. Now, this is by design a remote code execution vector. If you look at this example code down the bottom, what's happening is it's connecting to RMI, which is remote method invocation, another one of these protocols, and localhost 1099, which if you run Java anywhere, it listens to 1099 locally for RMI. And then it goes and looks up a class called foo. And the value of local obj will be set to an instance of the foo class as that class is defined by what's hosted on this remote method invocation server. So it's by design a remote code execution mechanism. And it's obviously implicit that applications should never look up a user-controlled JNDI string. The next country in that map was Spain. So Alvaro Munoz, another highly underrated security researcher, he presented this at Black Hat 2016, where, yes, we know that you shouldn't look up arbitrary user-supplied JNDI strings, it's obvious, but there's a whole lot more nuance to this. It's a fantastic paper, by the way. I would highly recommend going through it. But as an example of the kind of thing that he was able to demonstrate, in this case, you create a JNDI reference to a secure RMI server that you control. So you think, I've given it this contextual URL and it's only going to load methods from that server. But then if you give it essentially an absolute URL path in the lookup that's attacker controlled, it overrides that completely and just goes to the absolute path that you've defined rather than the relative path to that secure server. So what it implies is any way that an attacker, and this paper is really extensive, it's like 70 slides of hardcore technical stuff. Any way that an attacker can get a JNDI string into a context.lookup, they are going to get RCE. That's the conclusion of his work. Enter Log4j. Log4j is the most popular logging library in Java, and it's absolutely ubiquitous. So Java largely uses a dependency management system called Maven. There is an alternative called Gradle. And it's notorious for creating huge dependency graphs. Because the architecture of Java is that everything has been modularized into small components. Once you include one component, it's then got dependencies on another 10 that have dependencies on another 5 and another and all of a sudden you just wanted to include like Apache common file upload in order to upload some files, and now you've got 15 different libraries in your dependency graph. So large enterprise applications can easily have upwards of 100 dependencies in their graph. And I've never seen an enterprise application that doesn't have Log4j somehow in there because it's so ubiquitous. This is an ERD of the structure of Log4j. The main point is that it's got a contextual logging capability. And the philosophy of Log4j is that you should never have to use a debugger. You should contextually log everything because you can say this is a debug log, this is a normal log, this is a that log, that whatever. And you should never actually have to run your code through a debugger because you log everything verbosely. And that's what everybody does. So then enter Log4SHEL. And this is where we get to, I think, the last country in that map of the world, which is China. So Chen Jiaozhen, who found this vulnerability, identified that Log4j has a lot of advanced capabilities. You can use it to just log strings, but those strings are not just string literals. They contain an expression language, and that expression language can be used to bind variables, similar to the way that you might do something like bind SQL parameters in a query string or something like that. You can bind variables and, like a format string sort of thing. But it's got all this advanced functionality, and one of the things that you can do is actually give it a JNDI URI. And that JNDI URI will be resolved and executed. So an attacker who can control input into log messages or log message parameters can use that to inject a JNDI URL, which, as we then said, if you do a context lookup on a JNDI URL, you get remote code exec. And therefore, because everything is using Log4j, everything is logging something supplied by a user, everything is vulnerable. Here's some example code, which I don't know if is sufficiently visible in that shitty resolution. I apologize. But basically, it's that you have a HTTP server with an attacker-controlled variable that goes in. One of the variables that was very commonly used to exploit this was the user agent string. Because the user agent string is just a HTTP request header, but it's logged almost ubiquitously because everybody wants to do analytics to determine what browser everybody's using, right? So it's going to get into a log file somewhere. So just inject the user agent, that gets logged, and what you put in the user agent is this JNDI string. So this is what an attack chain looks like. You make a request including that string, and so those curly braces are how the expression language format within Log4j identifies that it's got a JNDI URI that it wants to interpolate. You pass that into the target server. It will then make a request back to that URL, which should point to a server that you control, which will host a malicious class. That malicious class will then be sent to the server and it will be deserialized. You get straight code exec. Now, going back to what we were talking about at the very start of this talk about how deserialization RCE works, this isn't the case here. This is literally just you define a class that has whatever you want in it, you pass a reference to it to the server, it goes and retrieves it, and then it deserializes your class and does whatever you want. It doesn't rely on any of that stuff that we spoke about earlier. However, that was only exploitable under a whole set of conditions. The application has to use a vulnerable version of Log4j. It has to log arbitrary strings provided by the user. Those are pretty easily met. There's no Log4j specific mitigations. So people were trying all these things like, I'll set this JVM flag at runtime to disable blah, 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 and it will fix it. And you had to have a specific version of the JRE or JDK that was vulnerable for it to work. Now, the reason you had to have a specific version of Java to be vulnerable was that they realized that there was an insecure default property. So this LDAP.object.trustURL codebase is the configuration parameter that allows, by default, you to just pass in an attacker-controlled JNDI URL and have it resolve, no questions asked. If this parameter is set to, this configuration parameter is set to false, that functionality will be disabled out of the box. And finally, after however many years of Java being around, somebody realized we should set this to false by default. And they did that before the Log4Shell vulnerability came out, but not sufficiently long ago that a lot of people weren't running vulnerable versions of Java. Now, as a brief aside to this, this is a common historical theme with Java, of having really bad insecure defaults. My favorite story is about XXE vulnerabilities in Java, because if you go back to 2003, somewhere on the Microsoft MSDN forums, there's some post in 2003 where somebody has recognized the XXE vulnerability class and said, hey, in the XML parsers, we should disable the expansion of external entities by default and only enable it when requested. And like a few months later, Microsoft are like, this is in MSDN patch, blah. And since then, it's been fixed in .NET, which is why .NET applications have hardly had any XXE vulnerabilities. Java apps, on the other case, had it enabled by default. And when this started to become a bit of a pandemic, circa 2012, of all these XXE vulns in Java, I tried to work with the Java developers to disable it by default. And they said, actually, we can't. Because the way Java's designed, you have these specifications that, I think they're called JSRs, Java Specification Requests, that define how everything will work. And because there's heterogeneous implementations of everything, there's like the HP JVM, the IBM JVM, the Open JVM, all these, the Sun JVM, Oracle JVM, they all implement this contract specification in order to be interoperable. And the contract specification had stated that you must expand external entities in XML parsers by default. So they couldn't patch the vulnerability because it would break the contracts, and hence you had this pandemic of XXE vulns in Java. So the point of the story was they've had a bad track record with this one. So what then was possible on these non-vulnerable versions of Java was you could go back to this original thing. You could go back to deserializing a class that existed. Because you could no longer deserialize a remotely supplied class, you could deserialize a locally supplied class, and then if that local class had, because this configuration parameter prevented you from loading your external code, but it didn't prevent you from pointing to a local class. And if you could point to a local class that contained an exploitable gadget chain, then you would land in RCE the same way that Takeshi Terada had figured out back in 2013. Bypassed all the controls and required them to reissue the patch for this. Now, this is my smug little moment where I get to say I told you so, because if we had actually patched all of the gadget chains as originally proposed and considered those to be a vulnerability, none of this would have happened. But because those gadget chains were left unpatched and the deserialization was considered to be the vulnerability, this whole thing was exposed to a broader audience than it needed to be. And that's the end of my presentation. Oh, you're on there?
Hello? Can you just call that audio?
Yeah, I can.
Hey, man. Yeah. So, yeah, Dave, that was a great talk, especially if you think of how things could have been different back in 2013 if things had...
It's an interesting what if, yeah.
And then people wouldn't be, like, renaming their Teslas and iPhones to JNDI, LDAP. We don't have any questions, but...
It's all right.
So it might be a great time to go early to lunch. I'm sure Dave would love to catch up outside.
Yeah.
He's a really smart guy, really great guy. So yeah, please thank David again.
Thank you, everybody.
Awesome, man.
Thanks, man.
Yeah.
Appreciate it.